Well, welcome back to Remote Sensing Applications using ArcGIS. This week we're going to have some applications using LIDAR rasters. And LIDAR stands for Light Detection and Ranging, and it's basically based on laser pulses which are used to create elevation point clouds or elevation rasters. And typically with LIDAR data we have either terrestrial elevations or water depths for clear water bathymetry applications. And LIDAR is available as very high resolution airborne data, and it's also available at lower resolution satellite sensor data. So for terrestrial applications, the LIDAR laser is used from the near infrared spectral region. So this is a color infrared photograph of an area, and then this is a raster of the first LIDAR pulse returned. So basically you're mapping the tops of the canopies. And most of the area is highly reflective in the near infrared spectral region, but here's a water body which is not reflective in the near infrared spectral region. So typically with terrestrial LIDAR, we'll have no data for clear water pixels, because basically we don't have that reflection from the clear water back to our sensor. So here's a hole of no data due to clear water, and here's another area where we don't have canopy elevation estimates because it's clear water, so it's no data. So LIDAR is typically provided to the customer in first return and ground elevation estimates. So this might be all the LIDAR returns for a single pixel. And the first return, this value would be stored as the first return for the pixel. And then basically one of these minimum values down here will be stored as the ground elevation. So if we took the first return elevation minus the ground return elevation, we would have what the estimated height of the vegetation canopy is for that pixel. So this week we'll have 3 applications using LIDAR, and we'll work in 2 study areas. So one study area will be the Tanana River floodplain, and the other study area will be the uplands a couple kilometers up from this Tanana River floodplain. So the uplands look like, so basically this is the Parks Highway, and then here's a black spruce stand, and then a young white spruce stand, a very dense young aspen stand, etc. So what we're going to do, the first exercise will be to assess the precision and accuracy of our LIDAR elevation estimates. So we'll have points along the Parks Highway, and then we'll buffer each of these points. And then since the area on the Parks Highway within this 2-meter buffer is flat, we would expect the ground elevation estimates from LIDAR to have low variability within each buffer. So what we're going to do is assess the variability of these ground elevation estimates within each buffer. And we'll do the same thing on the Tanana River floodplain. So since this is turbid water, we have LIDAR estimates of the elevation of this turbid water, because turbid water is highly reflective in the near infrared spectral region, and our LIDAR pulse is in that near infrared spectral region. So what we'll do is we'll buffer each point along the Tanana River, and then within these buffer, we would expect the LIDAR elevation estimates to have low variability. So the question is how variable is the LIDAR elevation estimates within each buffer? So we do that to assess the precision of our LIDAR estimates. We'll also assess the accuracy of our LIDAR estimates. So to assess the accuracy of an estimate, we are going to compare the true value compared with the estimated value. So our true value will have points that were recorded along the Parks Highway, and using highly accurate GPS methods, we have the actual elevation for each point. and then we'll compare that elevation for each point with the LIDAR elevation from our LIDAR raster. So then if we subtract the true value minus the estimated value, we get an error. So in the first case, our error was 7 centimeters. Our second point, the error was 9 centimeters. So basically we can get what is the mean error based on all these GPS points, and that will give us a picture of how accurate our LIDAR estimates really are for estimating ground elevation along the park's highway. Okay, our second application will be using LIDAR first return elevation minus our LIDAR ground elevation will give us the canopy elevation. And what we're going to do is find those pixels that are taller than 33 meters in height. So the canopy height will be above 33 meters, and those will be tall trees in most cases. So in this example, all these green squares are pixels that had a canopy height above 33 meters. And we'll do that application in the uplands, and then we'll do the same application in the floodplain. So basically we're going to isolate these tall canopy pixels and then convert the tall canopy pixels into polygons. And then basically we want to locate all these tall pixels or all these tall polygons that have a canopy height above 33 meters. Okay, and our final application will be to develop a raster representing percent forest canopy closure. So we can do that using a criteria that if a pixel has a canopy height above 3 meters, we will consider that pixel to be a forest canopy pixel. And then we'll make a block that's 10 pixels wide by 10 pixels high, and then within that block determine the total number of pixels that have a canopy height above 3 meters. And using that method, we'll come up with a forest canopy closure raster. So for example, here's a dense aspen stand, and it has a forest canopy closure of 98%. Here's the park's highway. It has a forest canopy closure of 0%. Here's an area that's sort of a mixed white spruce Alaskan birch stand with some canopy gaps. It has a forest canopy closure of 75%. So that's what we're going to do as our last LIDAR application, is come up with a map of percent forest canopy closure for the uplands and then also for the Tanana River floodplain study area. Okay, so if you go to the Blackboard website, I have a link for you for our first LIDAR application video session.